Got it? The audio, I'm good? All right. I will begin with a word of prayer. Dear Father, we thank you for this day. Thank you for the students. Just pray you be glorified in what we do this day, Lord. In your name I pray. Amen. All right, so I had an example for you guys, maybe two, and then I'll take homework questions the rest of the time, most likely, okay? So one of the things I wanted to derive, because I think it's interesting, is Kepler's law. And so what is, well, Kepler has how many laws? What are Kepler's laws? Have you guys ever heard of these? I think the one we're about to derive is Kepler's third law. One of Kepler's laws says that the planets orbit in some kind of orbital plane, right? So you got the sun in the middle, and then the planets orbit around the sun in some sort of particular plane. Like all of the planets are in this one plane of orbital motion, right? And they're all traveling in ellipses, right? Or maybe Kepler said circles, I forget. I think he said ellipses. And so the planets travel in these ellipses, and Kepler's third law says that the period of the orbit, the time it takes to go all the way around, is related to the radius of the orbit in a very particular way. And we're going to derive that in just a minute using Newton's universal law of gravitation and the centripetal force law. So could one of you guys get the other side for me? Somebody? I appreciate it. Thank you. So remember we said if an object goes in circular motion, so this is a bit of a cheat because the planets don't really go in circular motion. They go in more actually an elliptical motion. There's a certain eccentricity, right? It's kind of a squashed circle, right? But to a pretty good approximation, the planets go in more or less circular orbits. And so we have the situation, we've got the sun in the middle, yeah? Purple sun. It's also going to be a purple planet though, so, planet. Mass of the planet, mass of the sun, and you've got the distance here. Let's say big R. So let's say little r. I usually use little r for this. So little r is the radius of the orbit of the planet, and we're supposing it goes in a circle, right? Something like that. And so you can track the speed, v, which the planet's going, right? When the planet's over here, the velocity is going like that, but it's still the same speed. So the speed is constant around the circular motion, but the direction of the velocity is always changing, right? What keeps the planet going in a circle? It's the pull of gravity by the sun, right? What's the force of gravity look like? Like this, right? Gravity. And so what did we learn last time? We learned that, Newton told us that the force of gravity was equal to g, in this case, the mass of the sun times the mass of the planet divided by the distance between the center of the sun and the center of the planet squared. And according to mechanics, laws of motion here, we could derive with calculus and vectors and things like that if we had more time, and a couple of other math prerequisites. But setting that stuff aside, we have got mass of the planet, v squared divided by the radius. Little r, radius. So this is, mv squared over r is the mass times the centripetal acceleration, right? V squared over r is the centripetal acceleration. Certainly the planet has centripetal acceleration, center-seeking acceleration. So that's Newton's law, essentially, in this context, all right? Now, if it's going in a circle, what's the relation between the velocity and the period of the orbit? What's the relation between velocity? So velocity, or speed rather, is distance traveled, right? Over time, right? Elapsed. Ooh, I could almost say it today. So how about, let's think about a whole year, right? Go all the way around the sun and back again. Let's say that's a period for the orbit. Let's call that big T. So that's the time elapsed, the period of the orbit, big T. What's the distance traveled when you go one time around the circle? Circumference, right? This came up in my discussion of the geosynchronous orbit problem last class too. So that would be 2 pi r. 2 pi r, yeah? That's the circumference of a circle, radius r. And so I put these two ideas together, and that gives me Kepler's third law. So let's clean things up a bit here. So we've got g, mass of the sun. Oh, hey, before we go any further, what happens with the mass of the planet? Look at this. That cancels. That's kind of neat. That says that the orbit, in some sense, is not really connected to the mass of the planet. It's just a characteristic of the sun in some sense. Let's continue thinking about that. But GMS over r squared equals v squared over r, yeah? But what is v squared? That's 2 pi r over t, quantity squared, yeah? And we got to do some algebra here. What's this give us? We've got a 4 pi squared r squared divided by r squared, rt squared. All right. Let's see here if we can collect things together and make a nice, neat, tidy result. So if I move all the r's over there and all the t's over here, I've got that t squared, yeah, is equal to what? It's equal to 4 pi squared divided by g times the mass of the sun. And how many r's do I have left over on the right-hand side if I solve for t squared? Looks like I've got r to the 4th divided by r, right? So we could put r cubed here, yeah? So we could look at it that way. The square of the period is proportional to the cube of the radius of the orbit. Or we could also look at it this way. If you don't like that, you could look at it this way. R cubed is equal to g times the mass of the sun divided by 4 pi squared t squared. So either this or that. I kind of like that one, I guess. What did we say the units for the gravitational constant were last time? What did we figure out they were? It's kind of weird, right? You guys will have to help me out. I've forgotten what they were. Newtons times meters squared divided by kilograms squared. That was the units for G. That makes sense to me, sure. And we could rewrite that in terms of kilograms and meters in second, right? That's a kilogram meters per second squared times meters squared over kilograms squared. So we can simplify the units for the gravitational constant, like we did last time also, to a meters cubed divided by seconds squared times what? Kilograms, well, times kilograms, right? Because I got a meter squared times a meter, meters cubed, and I divide by kilogram, I got a second squared. And I think if you look at the units, it makes a lot of sense, right? So if I take g times the mass of the sun, that's giving me like, the kilograms are canceling, and I'm left with a meters cubed, and the second squared from the g constant will cancel with the t squared. The dimensional analysis works out for the boxed equation, is my point. So this is Kepler's third law. It says that the relation between the orbit and the period of the planets is independent of the mass of the planets and completely just depends on the mass of the sun, which is kind of neat, right? Now, if you want to work in terms of, let's see here, if we want to put the radius in if we want to, we could use, what's the distance from the Earth to the center of the sun? What's the mean orbital radius of the Earth orbit around the sun? What's that called? Does that have a name? You're like, you just called it the mean orbit of the Earth around the sun, right? That's true. I did that. I think it has another name, though. Let's see here. It is about 1.496 times 10 to the 6 kilometers. I want to say that's an astronomical unit. What's an astronomical unit? An AU. How big is that? Before I tell you wrong, let me check on the index here. You could, of course, Google this. You guys have phones. Let's see here. Astronomical. Come on, atomic, atom. I don't care about atoms. Astronomical telescope. That's no use. This book is, I hate this. Forget this book. It's no use to me. Can somebody Google astronomical unit for me and tell me how much that distance is? Do your English. He's looking at me. I think it's 1 point, yeah?
149.6 million kilometers. The mean distance from the center of the Earth.
Okay, so this is, and what's the symbol for it? Is it a?
It's 149.6 million. Oh, you put it.
Yeah.
What's your other question?
1.49 times 10 to the 6 kilometers? Mm-hmm. And was there a symbol for that? Like it's, no?
AU.
Yeah, I think it's usually 1 AU, astronomical unit. Anybody else hear that? Okay, all right. So if we use astronomical units and we use years, right? If we use the unit of t in years, then what's the value for g times the mass of the sun divided by 4 pi squared? What is, if I wanted to put, how many, this is g times the mass of the sun divided by 4 pi squared equals to what number times, goodness gracious, astronomical units cubed divided by years squared kilograms. Like what do I, fill in the blanks for me. What goes there? Can you tell me? Well, think about it, right? If the radius is 1 astronomical unit, right? How long is the period? By definition of Earth year, it's a year all the way around. So in other words, that coefficient, the thing in parentheses I haven't drawn yet, is just 1 if you work in these units, right? Which is kind of nice, because if then you ask questions like, okay, so suppose you had a planet orbiting the sun and you wanted it to have a year, the planet's year, all right, the time for the orbit of the planet around the sun to be 2 Earth years. What's the radius of such a planet, right? What is the radius for t equal to 2 years? Earth years, of course, yeah? So it's pretty simple. We just go, okay, well, we know that t squared is equal to, r cubed in, fine. 4 pi squared divided by g mass of the sun, r cubed. What don't I know? I don't know r. I'm trying to solve for r. I just wrote down the wrong equation, right? To make my life easier, I should have just written this one down, right? R cubed is equal to g times the mass of the sun divided by 4 pi squared rather, t squared. So what we're given what? We're given that we want the time to be what? 2 years. So what's this become? This becomes that's 4 astronomical units cubed when you work out the units, right? Because this, again, is a astronomical unit cubed divided by, there's no kilograms in this. What happened? How did I get kilograms in there? The kilograms cancel out in the, what units did I have for G last time? I had meters cubed over second squared kilogram. Okay.
You were using the kilogram for the M1 and M2.
Oh, I'm sorry. It's the. I'm an idiot. So, what the mass of the sun has what in it? Kilograms. Those kilograms cancel this. I'm supposed to just have. I'm sorry. It's my mistake is right here. I should just have g mass of the sun over 4 pi squared is equal to an astronomical unit cubed divided by a year squared. This simplifies calculations greatly for these problems, because otherwise you might find yourself doing things in terms of meters and seconds. Like there's some horrible unit conversions you'd have to do, right? You'd have to like convert a year to seconds or something, which you could do, but you'd like to avoid it if you could, right? So I'm trying to show you the easiest way to do this problem right now. Let me continue. So this is, again, this is a astronomical unit cubed divided by a year squared. And when we multiply that by 2 years squared, that just leaves us with 4 astronomical units cubed. And what's that tell me the radius of the orbit is? The cube root, yeah? The cube root of 4 astronomical units. So if I want to find a planet that has a year, quote unquote, for the planet, which lasts twice as long as the Earth's year, I need to look at an orbit that's away from the sun, the cube root of 4 away from the cube root of 4 times the Earth radius away, not Earth radius, but the Earth's orbit away from the center, where the sun is. What is the cube root of 4? I don't. Oh, here it is. That I don't know right offhand, honestly. Let's see here, cube root of 4, 1.587. 1.587 astronomical units. Now, if I want to convert that to meters, how much is that? 1.587 times 1.49. Where was it? 1.49 times 10 to the 6 kilometers, or we could say, yeah, we'll find times 10 to the 6 kilometers. I'll leave it in terms of kilometers then. So what you got? I have 2.365 times 10 to the 6th kilometers. So there you go. That's how far away from the sun you would find a planet, if there was such a planet, as a planet that had 2 Earth years as its, perceived year. There are planets with what? Longer orbits around this? I mean, there are planets that have quote-unquote years which are shorter or longer than Earth years. If we go further away from the sun, further out than where we are, is their year longer or shorter than ours? If R increases, does the T also increase? It does, right? So the bigger the orbit, the longer the year. The shorter the orbit, The shorter the orbital radius, the shorter the year, right? So what planet is closer to the sun than us? You can name one, right? Mercury, at least, right? Venus, is that closer? Yeah, so these would be planets that have shorter, quote-unquote, years. It takes them less time to get back where they started in their orbit around the sun. Yep.
So does this work for ellipticals and circles?
Yes, it turns out that you have to have the proper interpretation of what R means, but yeah, if you interpret R correctly, if it's I think it's a semi-major axis rather than the radius, but yeah. And the interesting thing about this Kepler, which came first? What's the chronology here? Was it Newton, then Kepler, or was it Kepler then Newton? Like which one predates the other?
Kepler.
Yeah, Kepler is the forerunner. So Kepler had the good fortune of being essentially the lab assistant for a guy named Tycho Brahe. Tycho Brahe, colorful figure, lost his nose in some sort of sword duel of some sort. Somebody chopped his nose off. If you believe the rumors, he died early, well, somewhat early, due to some unpleasantness, let's say. And so then, Kepler is working for him. And so Tycho Brahe was a fantastic astronomer. He had taken 2 decades of meticulous measurements of where the planets were in the sky and how they're orbiting and what's going on, yeah? So basically Kepler had 2 decades of just amazing data to work with. And Kepler just sat and figured out that you could explain the orbits of the planets if you thought of them, first of all, the Copernican idea that the sun is in the center, right? As opposed to the old idea, which was what? That the Earth was in the center, right? I mean, it's not wrong to say that the Earth is in the center from one frame of reference anyway, right? Like, is the Earth in the center for our current frame of reference? We're on Earth, right? So, yeah, it's just from another frame of reference, the sun is in the center. I mean, it depends on how you want to look at things. Anyway, if you are looking at things in terms of the sun being in the center, which is the more natural thing in terms of studying the motion of planets, then Kepler figured out if you put the sun in the center and you imagine that the planets orbit in ellipses in this orbital plane, then it fits the data. Like, it makes sense, actually. And this was actually very annoying because at the time they were looking for circles, because circles had perfect symmetry, right? So people were not entirely enthused in this elliptical thing. They would rather have had circles, so they invented these things called epicycles. You know what epicycles are? Epicycles are like circles on top of circles on top of circles. It turns out if you're a sufficiently creative fellow, you can reconstruct elliptical orbits in terms of one circle superimposed on another. So you have a circle, and then you have another circle on top of that, and you put the motions together, you can generate all kinds of crazy patterns. So, I mean, you could imagine this if you could look at a merry-go-round and you had like a kid holding a hula hoop and like swinging it around, while he was traveling on a merry-go-round. And if you actually watched like a point on the hula hoop and the kind of path it could trace out, you'd quickly realize that you could make all kinds of fantastic paths, including something as boring as an ellipse. So epicycles were a popular thing because they're built with circles upon circles, which were perfect symmetry. But physics seemed to suggest that, in fact, the orbits were elliptical. That's what Brahe's data and Kepler's analysis revealed. And then about, let's see, I think that was, oh goodness gracious, my history. I don't want to say it's that 16th century stuff. We're talking like 1500s that this went down. And then when did Newton come out with the universal law of gravitation? That was a 17th century thing, right? Mid-1600s, 1660 to 1680, somewhere in there. Not sure exactly. But when he was about your age, he came up with some of these ideas, and he realized that there's one universal notion of mechanics, which when you add laws to it, they obey regular mathematical patterns. And that's what this course is about, right? Working in Newton's framework of force F equals ma and seeing how things work out. And I think it's pretty neat that this small whiteboard of calculation can recover what it took Tycho Brahe and Kepler the better part of 2 decades of careful, there was their life's work to discover this, right? We have used essentially college algebra in 10 minutes to just kind of discover it for ourselves because, well, we got to start with what Newton gave us, right? Which is the law of gravity and the centripetal force thing, which is like super, super nice. So anyway, I'm going to shut up. You guys have questions about your homework, go for it. I had one other example about a binary star, but maybe I'll save that for some other day, or your test. So anyway, it's a joke. Yes? Okay, so the astronomical unit, this is a definition. So that's like asking me how I defined a mile to be 5,280 feet. I mean, I didn't do it. In the same way, I didn't do this either. This is just a thing, that the distance from the average distance from the center of the Earth to the center of the Sun is defined to be an astronomical unit.
So how can we replace the G and the mass of the sun and all that for the AU?
Ah, very good. So it's the observation that if we put 1 astronomical unit cubed here, right, and we put over here 1 year squared, right, what has to be here? I mean, the thing is, I know it takes a Earth year for the Earth to go around the Sun 1 orbit. So that means that in these units of years and astronomical units, this proportionality constant must just be 1. Does that make sense?
So is the AU supposed to be the distance that the Earth orbits the sun? Is that what an AU is?
Yes, the distance that the Earth orbits the Sun. Now, we could work out this constant. Good exercise. Let's work it out the other way. G times the mass of the Sun divided by 4 pi r squared. 4 pi squared, rather, right? Let's work it out. So this is 6.67? Am I right? 6.67? Oh, it's starting to stick again. That's not good. Times 10 to the minus 11. Mass of the Sun, it's like, I don't know, 1.99 times 10 to the 30th. All right? And you got divided by your pi squared. And this is going to be in units of kilogram. Well, excuse me. What was the silly units here? Meters cubed over seconds squared times kilogram, yeah? So we can figure out what that number is, right? What is it? I get 3.362 times 10 to the 18 meters cubed over seconds squared. Let's see if that agrees with my claim, which is that that's also equal to an astronomical unit cubed, yeah, divided by a year squared. So what do we got to do? We got to do a unit conversion, right? So an astronomical unit is 1.49 times 10 to the 6 kilometers. So we could say 1 astronomical unit divided by 1.49 times 10 to the how many meters? 10 to the 9th meters, right? Because if it's 1,000,000 kilometers, it's 1 billion meters. So yeah, the distance from the center of the Earth to the center of the Sun is about 1.5 billion meters. Like not the British billion, but the US billion. All right, that cubed times, how long is there in a year? How many seconds in a year? Oh, I'm sorry. I'm not. I'm not doing this right. I should be multiplying that up top, right? I'm sorry, guys. I'll get with it eventually here. That divided by an astronomical unit. That's. Sorry. Give me a second here. I'll get with the program. I'm trying to do a unit conversion. I should be multiplying by 1 as appropriate, right? So my first number 1 is 1.49 times 10 to the 9th meters divided by an astronomical unit, right? That will convert my astronomical units to meters. To convert years, I should do 1 year is how many seconds? How about 365 times 86,400 seconds? And that's something I'm supposed to square that. Where did I get 86,400 from? Yeah, 24 times 60 times 60 is 86,400. I said 24 hours times 60 seconds times 60 minutes is 86,400 seconds. That's the number of seconds in a day. Which is something that's permanently lodged into my memory because I've spent an inordinate amount of time of my adult life doing physics problems. Yeah? Okay, so like it's just stuck in my brain, this 86,400. Now I do not remember the number of seconds in a year, but it is a big number. 31,536,000, right? So this is 3.1536 times 10 to the 7th seconds. All right, so we got to take that and square it, reciprocate that, and multiply it by 1.49 cubed. I'm just calculating this thing, guys. And then I'm supposed to multiply that by 10 to the 9th cubed, which would be 10 to the 27th. And after all of that is done, I get, oh man, son of a motherless goat. Let's see here, 3.326. I have inadvertently lost something. I got 10 to the 12th meters. Okay, so I'm missing, I'm missing a, can somebody tell me where I missed the multiplier? Because I'm missing like a copy of 10 to the 3rd somewhere. I'm not sure where I lost it. It could just be in my calculator work. Did you guys get that, or 10 to the 18th when you worked it out? I like the numbers. They're very close. You got 10 to the 12th? Dang it. Did I miscalculate the one up above? What's the mass of the sun?
1.99 times 10 to the 30th.
Ah, curses. I remember that right.
Is the 1.49 times 10 to the 9th supposed to be 1.49 times 10 to the 6th?
Well, that would be kilometers, though. So I tried to convert it to meters. I don't know where I've made my mistake, guys. Give me a second here. Yeah, I got the same number again. I definitely getting 10 to the 12th there. Is my I think my unit conversion's right. I'm not sure where my mistake is at the moment, guys. What's 6.67 times 10 to the minus 11th? Well, my value for G is right. Mass of the sun is right. Woo! I'm sorry, guys. I don't know what the error is at the moment, but there's clearly something at odds here, right? We're off by a factor of 1,000,000. So, which, in a nutshell, illustrates why I like to use astronomical units and in years, because we avoid this kind of insidious error. You know, if I wanted to find a orbit which had, I don't know, 3 Earth years, then I would be looking for what? You know, the cube root of 8. I would need 2. You know, if we went out to the radius of the planet orbiting being 2 astronomical units, then you'd have a year for that planet, which would actually be 3 Earth years, for example. All right, I'm going to stop talking about this because you guys have questions, I think, besides this. So, listen. So, whoever can clearly explain the error here, 5 points. Don't tell me now. Email me. First person to email me clear explanation for what went wrong here. 5 points. Not enough? 10 points. Let's get nuts. 10 points.
What is the exact error we're looking for?
Why the
How? Like these should be equal. Because allegedly, G times, you really don't want to keep asking me this, because in the process of talking about this, I might solve it. It's a danger. It's a danger. But G times the mass of the sun over 4 pi squared, by an argument I gave over here, that should just be equal to 1 astronomical unit cubed divided by year squared. So, yeah. Can you do it in a group and share the points? Interesting. Let's take a vote on it. What do you guys think? In favor of the group possibility of group points? Not in favor of possibility of group points? Don't care one way or the other. Oh, that's the dominant viewpoint. All right, since the people who care about group points are in the majority of caring, I'll say sure. Yes, you could share the points. Why not? So if like 5 people solve it, then it's like 2 points apiece. Do you guys have questions about homework?
I could not figure out, where was it? Page 69, number 27.
Number 27 on page 69.
Yeah, part D. And you can do the whole problem if you want.
Yeah.
But part D, I couldn't.
A projectile is fired with an initial speed of 36.6 meters per second at an angle of 42.2 degrees above the horizontal on a long flat firing range. Determine the maximum height reached, the total time in the air, the total horizontal distance covered, that's the range, and the speed of the projectile 1.5 seconds after firing. Oh, this is not bad. I think we can use, I mean, it's the same initial and final height, yeah? So to figure out the range, we can use the range formula, yeah? All right, so let's work it out here. Again, this is number 27 from page 69. Here's the deal. You've got initial angle of 42.2 degrees, yeah? And you're given the initial speed is 36.6 meters per second. Long flat firing range they want to know a few different things, right? They want to know what's the range equal to? Yeah. They want to know what's the max height equal to? What else do they want to know? Max height. Oh, they want to also know the time, the total time, right? The total time it takes, yep.
I figured out why that was. I did too.
Who will email me first and get the points?
Oh, I can't do that.
I'm just kidding. You just email me. Don't say it out loud because then I'm going to get 30 emails. All right, actually, you should tell me so we can settle it while the video's running.
The original, it should be 1.49 times 10 to the 11th meters instead of 9.
Oh, so you guys tricked me about the, and so that's very comforting actually. So it was 100. You told me 149 times 10 to the 6th, and then I wrote down 1.49. There's the error. So 149 times 10 to the 9th meters would be correct, but 1.49 times 10 to the 11th is the same, right?
I told you it was 149.6 million.
So 149.6, and I just heard 1.49. So I just, yeah. And I dropped the 6 altogether, which probably explains why this number is a little bit smaller than that number. Yay. All right. Sorry, your group should have worked faster. See here. Small lesson about the value of group work right there. Small lesson. All right, so just say it. So total time in the air, total horizontal distance covered, that's the range, and the speed of the projectile. Are you stuck on part D?
Yes.
You got everything but D, right?
Yes.
Yeah, okay. So D, that's the part that's a little bit sneaky. Speed of projectile at, what is it? At what? T equals 1.5 seconds after firing. So let's put T equals to 0 right here, right? Okay. So what do we know? Let's see here. So here are the equations that we know. We know that x is equal to 36.6 meters per second times the cosine of 42.2 degrees times time. See, because this number multiplying time is the initial x velocity, right? By the way, Vx is equal to 36.6 times the cosine of 42.2 meters per second for the whole time, right? That is the constant x velocity of the projectile because there's no acceleration in the x, right? So whatever x acceleration you give it to start with, right? So hi. Okay. Whatever x acceleration you give it to start with, and to be careful, I'll make sure I'm in degree mode here, right? 42.2, 30, stupid fingers, not working. That was a problem. All right, 27.11 meters per second is the constant, goodness gracious, 27.11 meters per second. There you go. That's the x velocity for all time in this problem, right? How about y? What's the deal with y? Y is 36.6 meters per second times the sine of 42 degrees, 0.2 degrees times time, minus 4.9, meters squared per second squared, rather meters per second squared times t squared, since I'm putting in these units. Right? This is the equation for, there's an acceleration in the y, right? Minus 9.8 meters per second squared. So we have the 1/2 at squared term, right? Which is minus 4.9. Now the y, how about y velocity? Vy is let's see here. Let me work out this number. What is this number? I get 24.58. 24.58 meters per second is this guy right here. Right, so it's that minus what? Minus 9.8 meters per second squared times time. So that's the formula for the y velocity. So other people here are probably curious how you find the range and the max height, right? We actually derived formulas for those things. We could use them here if we wanted to. What was the formula we had for R? Do you remember? What was it? It was V naught squared sine 2 theta over G, which in this case is what? 36.6 meters per second times the sine of, well, 2 times theta is 84.4 divided by 9.8 meters per second squared, yeah? So what's the range? 136, I heard. Is that the answer in the back of the book?
They put it with their significant.
Oh, with sig figs, yeah. Their sig figs are insignificant to me. All right, so one, I'm just going to give you 4 numbers and ignore the sig figs. You can, my apologies for those of you who care. So there you go, the range. I got 136.0. Is that what you told me? Okay. And how about Wimax? What was the formula for Wimax? Do you guys remember? It was V naught squared, I want to say, was it sine theta? I cannot remember. Is it sine theta over G? Sine squared theta. Oh, sine squared theta. And divided by G? 2G, right? 2G. We worked that out the other day. Let's use it now. So we've got 36.6 quantity squared times the sine of 42.2 squared divided by 2 divided by 9.8. I get 30.84 meters, yeah? So there's the max height, roughly speaking. Again, we have worked out why these formulas are true the other day, right? Been a few days, but we did it. Remember back before that hurricane happened. All right, didn't happen here. Anyway, what else do we need to know?
Did we ever figure out part D?
And so we got A, B, and C. Oh, what's the total time? How do you figure out the total time for flight? If we've already got the range and x, we could figure out total time by what? How about this? 36. Well, how about this? 27.11 meters per second times the total time equals what? Equals the range, right? So if you've already calculated range and you know the x velocity, it's easy to find the total time. It's just range, which was 136 divided by 27.11. So I get a total time of what? Roughly speaking, 5.02 seconds. All right? You're like, fantastic. You've told me everything I already knew. But what about part D? What is part D asking you? It's asking you for the speed, right? The speed. What's the difference between speed and velocity? Speed doesn't have a direction is definitely a good answer. They're related though, right? What is speed as it relates to velocity? What is speed? Speed is the magnitude of the velocity vector, right? So if I want to draw a picture, if this is the velocity, you know, this might be the x part, this is the y part, right? We could put an I hat here, we could put a j hat here. You know, the velocity is the vector sum of the x component of the velocity and the y vector component of the velocity. The speed is the magnitude. I use these double bars before, I think. It's the magnitude of the velocity, which is equal to the square root of vx squared plus vy squared. So that's the speed. The speed is the square root of the sums of the squares of the x and y components of the velocity. So to answer part D, right, to answer part D, we have to figure out what are the x and what are the y components of the velocity, right? Well, vx we already know, it's constant. It's 27.11 meters per second, always and forever, right? What's the y component to the velocity? Well, we're at what time? So we could say Vy at t equals to what? 1.5 seconds, right? So that is 24.58 meters per second minus 9.8 meters per second squared times 1.5 seconds. What is that? Whatever that is, that's the y component to the velocity. Still not the speed. Still not the speed, but getting closer. I get 9.88 meters per second, right? So you put these together, and we've got a speed, which is the square root of 27.11 squared plus 9.88 squared meters per second, which is to say that v is equal to, let me punch the numbers here, I get 28.85 meters per second. So ignoring their sig figs, I should more or less match their answer, yeah? Yep. Yay!
Thank you.
I still know physics. What do you know? Sometimes. If I can. What he's doing. Sorry. I'm easily distracted, as you know. Any other questions? Yes, sir. I will make a video that does both of the quiz problems, hopefully later today. I had somebody take the quiz late. That's why I haven't made the video yet. But now that that person's taken the quiz, I can make the video and hopefully post it for you guys later today. But a very reasonable question. Anybody have another question? Let's ask. We've spent enough time on projectile motion. I'd like to have a question from the force material, all right, or the gravity material. If you got a question there, that'd be better. Yeah. Number 27 from chapter 5, number 27. Uh-oh. Okay. It's worried me that this has a star here. You're like, well, you recommended it, so that's your problem, right? Fair enough, you got me. So what were we just saying? Number, what was it? 27. Didn't I just work number 27? Hey, what's up with you guys? Number 27 today. Number 27 from page 133. So this is all number 27 is the theme for today, apparently. Particle revolves in a horizontal circle of radius 1.95 meters. Whee! All right, so radius equals to 1.95 meters. All right, great. At a particular instant, its acceleration is equal to 1.05 meters per second squared. In a direction of 25 degrees, well, I lost it, 25.0 degrees to what? to its direction of motion. All right. Determine its speed. Right. And what else? And B at t equals to 2.00 seconds later, assuming that the tangential acceleration is constant. All right, so I don't actually. Let's say. Let me put it this way. I will not test you on Part B. Part B, I don't think belongs yet in the course. Part B, maybe we come back to later in the course. All right. To answer Part B is to answer a question in the kinematics of circular motion, which is a topic we discuss a little bit later in the course. At the moment, we're just talking about centripetal acceleration and just a little bit about tangential acceleration. So that's the purpose of this problem. And so let me try to explain that to you. So here's what's going on. We've got, I'll draw it up here because it's where I draw best. But you know, if the motion's like this, if we're going in this kind of motion, then the direction of the motion is like this, right? This is the direction of motion. The direction of motion is another way of saying the tangential direction. The direction that something would be going if the string that was holding it in a circle broke and it just went flying off, right? Like David Stone from the slingshot, you know, right? So after the stone leaves the slingshot, it just travels, you know, along the direction it's going. Anyway, we are told that the acceleration is 25 degrees to its direction of motion. Now that has to be like this, and I'll tell you why in a second here. That has to be like this. This is the picture for the acceleration. This angle is 25 degrees. And so the reason for this is that acceleration has two vector components. All right? The two vector components to acceleration are the center-seeking part, which is what kind of keeps it going in a circle, and the tangential part, which describes how the circular motion may be speeding up if it is. So here's the acceleration for constant speed circular motion. Constant speed circular motion, I can draw the acceleration vector for you any point in the motion. It just points towards the center. And if I'd done this right, these all should have the same length. So the acceleration is just v squared over r, center seeking. This is constant. If the v is constant, if the speed is constant, then we just have center seeking acceleration all the way around, right? This problem is about a hypothetical situation where you don't have constant acceleration. You don't have constant speed circular motion. You've got variable speed circular motion, which is coming from an acceleration which is not purely center seeking. There's part of it which is tangential, is the idea here. So if you look at the geometry here, let me use some color coding. We can break the acceleration into two pieces. We've got the center seeking part of the acceleration, right, which I could call a sub c. And we've got the normal part of the acceleration, or the tangential part of the acceleration, which I could call a sub t. But these are perpendicular, so we've got a nice little right triangle. Here's the relation. The net acceleration, the magnitude acceleration squared, is equal to the centripetal acceleration squared plus the tangential acceleration squared. This is the, I mean, it's a right triangle trigonometry. It's Pythagorean theorem again. And furthermore, you're given, what are you given? Oh, but you also know 25 degrees, right? Let's see here. Can you draw 25 degrees in that triangle anywhere? Where is it? Yeah, it's down there too, right?